Hi dear students, we start our discussion on the passage of alternating current through inductor and resistor. That is, we have a circuit that consists of an inductance and a resistance that is connected to an alternating voltage source. The inductor is L, resistor is R, and the applied voltage is alternating voltage, that is E0 sine omega t. In this session, we will derive an expression for the current, that is alternating current flowing through the circuit, and the power in the circuit, and also the impedance of the circuit. Fine. Now, if this alternating voltage is supplied to this circuit, the voltage developed across this inductor is EL, the voltage developed across the resistor is ER. Then, to solve or to find out the value of this current, impedance and the power in the circuit, the simplest method that we have already discussed, the different method to solve the problems in the circuit. Here we use the phasor diagram. Using phasor diagram, we will find out the value of the current, the impedance and also the power in the circuit. We know the phasor diagram in the case of a pure inductor circuit, that is, the voltage leads and the current lags. If there is a inductor, that is L, we have to remember that in the inductor the voltage leads. Therefore, the phasor diagram, we have to write the voltage through the inductor, that is EL, that leads the current by an angle 90. This we have already discussed. This is phi E is equal to pi by 2. The voltage leads, whereas the phasor diagram of the resistor, that is, both the current and the voltage both are along the same direction. There is no phase difference between the voltage and the current. With this information, we can draw the phasor diagram of this LR circuit. On the x-axis, we have the voltage across the resistor, that is VER. The voltage across the inductor, that is leads, that is the positive y-axis EL. The net voltage in the circuit, that we can draw this one, that is, this is the net voltage in the circuit. Then the angle between this net voltage and the current, that is the phi. Here the current is also along the same direction as that of the voltage in the case of the resistive circuit. That is, the phi is the angle between the current and the net voltage in the circuit. Then, if you refer this figure, length, this is nothing but this length. This is nothing but EL, and this length, this is nothing but our ER. Then, this net voltage, I will write this as a, instead of E, instead of V, I will write this is a E, because everywhere we have used the notation E for the voltage. Therefore, E is the net voltage in the circuit. Fine. Therefore, by looking at this figure, this phasor diagram, by using the geometrical method, I can write this is a hypotenuse That's the net voltage, that is hypertenuse square, E square is equal to EL square plus ER square. This hypertenuse square is equal to this ER square plus this EL square. That is, this E square can be written as EL means the voltage across the inductor. The voltage across the inductor can be written as I into the resistance, that is impedance offered by the inductor is IXL. The voltage drop across the resistor is I into R. If I substitute these two values here, this will be I square XL square plus this is I square R square. Then the I square is common. I take it outside, that is E square is equal to I square into XL square plus R square. If I take the square root, this will be E is equal to I into root of R square plus XL square. We know the Ohm's law. The Ohm's law, V is equal to I into R, or E is equal to I into R. Then the resistance is equal to E by I. Fine. Then here if you divide our E by I, in the present case we will get this is the root of R square plus XL square. This E by I, that is nothing but that is equivalent to the total resistance offered by the circuit, that we call it as a impedance of the circuit. Therefore here I can write this E by I is nothing but impedance Z, that is root of R square plus XL square. We can say that this Z is the impedance of LR circuit. Fine. In this circuit, if you look at this phasor diagram, it is very clear that the voltage through the inductor, that is EL, leads the current. Or we can say the current, that is that the current lags behind the voltage here by an angle phi. Fine. Therefore we can write the expression for the current here as I is equal to I0 sine omega t minus phi, because here the current lags behind the voltage. The voltage can be written as E0 sine omega t. Fine. Then if this is the expression for the current in the circuit, then I can write the power. The power in the circuit can be defined as voltage into current. This E is nothing but the applied voltage, that is E0 sine omega t. Here the voltage is alternating voltage. The current in the circuit is just now we have written, that is this quantity, that is I0 sine omega t minus phi. That is, this power is equal to E0 I0 sine omega t into sine omega t minus phi. Fine. Here we are discussing the passage of AC through the LR circuit. The AC means that we have this form, that is the current or the voltage have this form, that is we are always interested to find out the average value of the AC through this LR circuit. Therefore, we are interested to find out the average power dissipated in the circuit. The average power is the total power per unit cycle. Okay. Here, unit cycle means one cycle is completed for a time period T. Therefore, we are interested to find out the average power when we are dealing with the passage of AC in a circuit. Therefore, average power is defined as 1 by T into 0 to T, that is total power dissipated in the cycle 0 to T divided by the T. Fine. That is, if you substitute this P here, therefore we can write this is as a 1 by T into 0 to T E0 I0 sine omega T into sine omega T minus phi into dt. Fine. Here this E0 and I0 are common, we can take it outside. E0 by I0 by T into 0 to T sine of omega T into sine of omega T minus phi dt. This equation is nothing but sine A minus B. That is, we can write, therefore we can use that relation. This is sine A cos B minus cos A sine B. Okay. That is, in the next step I will write E0 I0 by T into 0 to T sine omega T into sine A cos B, that is sine omega T cos phi minus cos A, that is cos omega T sine phi dt. Then multiply the sine omega T with each term. That is, you can write E0 I0 by T into 0 to T. The first term is sine square omega T cos phi dt. Then here I put one bracket also, because we are splitting the above step into two. That is, here we have the minus 0 to T. If you multiply with the sine omega, this is a sine omega T cos omega T into sine phi into dt. Fine. In the next step, here, if you look at this, the first integration with respect to dt. Therefore, this cos phi is constant here, and in the second term, it is also the integration with respect to dt. Therefore, the sine phi is constant here. We can take this sine phi outside, here the cos phi outside of the integral. Then I will obtain E0 I0 by T in the first term, cos phi outside, then 0 to T sine square omega T dt minus here sine phi outside, then 0 to T sine omega T cos omega T into dt. Here, to do the integration, this can be replaced by, that is, sine square omega T, we can replace, this can be written as 1 minus cos 2 omega T by 2. That is, sine square theta is equal to 1 minus cos 2 theta by 2. And this time, that we can replace, that is sine 2 theta is equal to sine theta cos theta. Therefore, we can write sine 2 omega t is equal to 2 sine omega t cos omega t. Therefore, we can write this sine omega t cos omega t, that is divided by 2. Fine. In the next step, the average power, that is equal to E0 I0 by t cos phi integration 0 to t 1 minus cos 2 omega t by 2 dt minus sin phi. Here inside the integral 0 to t, instead of sin omega t cos omega t, we can write sin 2 omega t by 2 into dt. If you check this integral and the second integral, here 1 by 2 we can take it outside, then this integration, that is 0 to t 1 minus cos 2 omega t dt is here, that I can write 0 to t dt minus 0 to t cos 2 omega t dt. This is nothing but a t, and this is cos 2 omega t is sin 2 omega t. Sorry, this integration limit should be capital T, cos 2 omega t by 2 omega, and if you apply the limit, this will be t. Fine. Then this will be t minus sin the omega, we can write 2 into 2 pi by t into t, because this omega can be written by 2 pi by t, and in the denominator we have the 2 omega, but here you will see that this t and t cancel, then here we have sin 4 pi, the value of sin 4 pi is equal to 0. Therefore, you are left with t. That is 0 to t 1 minus 2 cos omega t is equal to t. And here the second integral, you have that 0 to t sin 2 omega t dt. Then if you do the integration, minus cos 2 omega t by 2 omega, here we have the limit is 0 to t. You can take a minus outside, or minus 2 by 1 by 2 omega outside, and this will be cos 2 into 2 pi by t into t minus cos 0, because apply the limit for the t first here, that is this step, then you apply 0 to t here, this step, then this is equal to minus 1 by 2 omega. This is a cos 4 pi. Cos 4 pi is equal to 1. Then cos 0 is also 1. Then this term finally goes to 0. That is, if you come back to this integral, this p average, here this term goes to 0, and this term gives the answer, that is t. Fine, this is the value t. Now we are left with this term only, that is, I will write in the next step p average, that is equal to E0 I0 by 2, and here you have this cos phi, and here you have the t, that is cos phi into t, cos phi into t. Oh, here one t is also here, that I missed. Here we have that t also in the denominator. Here the t and this t were cancelled. Then the final expression for the average power, that is equal to E0 I0 by 2 into cos phi. Okay, we can write this expression in another way. That is, you have already learned the RMS value of the voltage and current. The RMS value of voltage means it is ERMS, that is defined as peak value of the voltage divided by root 2, and the RMS value of the current, that is the peak value of the current divided by root 2. Its physical meaning is this one. The RMS value of the voltage or the current, that is defined as the value of the DC contained in the AC current or voltage. This is nothing but the value of DC in AC. Okay, this is the definition of the RMS voltage and current. If you write our equation according to these two equations, that is P average can be written as E0 by root 2 into I0 by root 2, that is, I write this equation in this fashion, and cos phi. This E0 by root 2 and I0 by root 2 is nothing but the RMS values. Therefore, P average is equal to, this is ERMS, this is IRMS into cos phi. Fine. This is the average power dissipated in the LR circuit, where this cos phi is the power factor. Here, if you know the value of this phi, that can be easily found out from this phasor diagram. If you come back to this phasor diagram, that is here, if you look at this expression, that is this angle phi. If you write the cos phi is the adjacent side, that is ER, divided by hypotenuse, that is E. This ER is nothing but I into R. E is nothing but current into impedance in the circuit. This cos phi is nothing but R by Z. Fine. That is, we can write this cos phi in the LR circuit is R by Z. Here, one thing I forgot to mention, what is the value of this Z? What is the expression for this Z? That is, Z is a total impedance offered by the LR circuit to the flow of AC through that circuit. Okay, that is the total impedance. If you come back to this equation, that is here, this is that impedance, the impedance of the LR circuit. Okay, this is nothing but the total resistance offered by the LR circuit for the flow of AC through that circuit. Fine. Now, in terms of the R and Z, if you replace this cos phi, then the average power can be written as V average is equal to ERMS into IRMS into R by Z. This Z is nothing but total impedance, that is R square plus XL square, or this R square plus the impedance offered by the inductor, that is nothing but L square omega square. Here, this is another representation, and this can also be written in another form. You know that E is equal to I into Z, then this E by Z can be written as I. Then if it is an RMS value, this will be ERMS and this will be IRMS. Then here I modify this equation in this way. P average is equal to ERMS by Z. This I take this Z with ERMS. This will be ERMS by Z into IRMS into R, then this ERMS by Z, it is nothing but IRMS. Therefore, the average power in the circuit can be written as P average is equal to IRMS into IRMS into R, or we can write the P average is equal to IRMS square into R. This is another representation of the average power. This is better in the circuit. Okay, this is equivalent to, we know that the average power in the case of the DC circuit is I square R. Both equations are in the same form. This is a discussion about the AC through an LR circuit. Now we discuss the alternating current through capacitor and resistor circuit. That is AC through capacitor and resistor. The circuit consists of a capacitor and a resistor. An alternating source of voltage is connected. This is a C, this is R. The applied voltage is E0 sin omega t. As I mentioned in the previous lecture, we know that the phasor diagram of the voltage and current in the case of a capacitor circuit, that is, in the case of capacitor, the voltage lags. Therefore, the voltage across the capacitor is EC, that is come down along the negative y direction, and the current is along the positive x direction. Here there is a voltage that there is a lag of the voltage by an angle pi by 2 with respect to the current. Fine. The voltage across the resistor is ER and the current is around the same direction. There is no phase difference. Therefore, the phase difference here phi is equal to 0, but here we have certain phase difference. Then in the combined RC circuit, the phasor diagram we can draw like this. That is, the voltage across the resistance is this one. The voltage across the capacitor lags behind the current by certain angle. Therefore, we have plotted in the negative y direction, that is, this is a capacitive voltage, the voltage across the capacitance, and the net voltage in the circuit, that is denoted by E. Here the current that is along this x-axis always, then the angle between this current and the net voltage is E phi. Angle is a phi. Then this distance, that is nothing but this EC. Therefore, this is nothing but EC, and this is the ER. Therefore, I will write this has the same length. This is ER. Using the geometrical method, we can write the net voltage in the circuit, that is the hyperteneous square, this E square, that is equal to adjacent side square, that is ER square, plus opposite side square, EC square. ER square plus EC square. In this case also, that is AC through the C and R circuit, here also we are addressing this question, that is, we are finding out the value of the total current in the circuit, total impedance in the circuit, total power in the circuit. Fine. For this, the simplest method is to solve this phasor diagram. That is, using this phasor diagram, one can easily find out this power, voltage, current, impedance in the circuit, and also what is the phase angle, that we can also easily find out. The voltage across the resistance is I square R square. EC is the current I square into resistance square, that is XC. Xc is the capacitive reactance. That is, we have already discussed in the last lecture, that is 1 by L omega. This is our E square. That is, from this equation, I square is common. I take outside the bracket, then this will be Xc square. Then if I bring the I square left side, this is E square by I square. This is R square plus Xc square. If you take the square root, this will be E by I. Then the right hand side also we have to take the square root, R square by Xc square. This E by Z, that is, this E by Z is the total resistance offered by the RC circuit to the flow of AC. That is, we can say the impedance of the circuit Z. That is equal to root of R square plus, instead of this Xc, we can substitute 1 by C omega. Xc square means C square omega square. Fine. This is the total impedance offered by the RC circuit to the flow of the AC current. We can say, simply we can say this is the impedance of RC circuit. Fine. Now, what will be the current? The voltage we know, E0 sine omega t. Since it is a capacitor, we know that here the voltage lags. Voltage lags means here the current leads. Current leads means we can write this I as I0 sine omega t, that is the current leads the voltage. Therefore, here I write plus phi. This trick I have already explained in the last lecture. What is this I0? I0 is nothing but this E0 by Z. E0 by Z means E0 by Z is a total impedance, that is R square plus Xc square. Xc square is nothing but 1 by C square omega square. Okay. Now let me define the phase angle phi. If you look at this picture, here you can, that is this phasor diagram, you can write this tan phi. Tan phi is equal to opposite side by adjacent side, EC by ER. This EC is nothing but I into XC, ER is I into R. This I and I cancelled. Therefore, this tan phi can be written as tan phi is equal to XC by R. This is 1 by RC omega. This is the phase angle phi, that is the phi is tan inverse 1 by RC omega. Okay. Now we can also find out the expression for the power factor or the power. Let me define first power. Power in the circuit is also same, that is P average, that is we always find out the average power, E RMS into I RMS into cos phi. Here this cos phi is our power factor, that is power factor cos phi, that is we have to find out the cos of the angle phi. Once again come back to this picture, that is from this picture cos phi is equal to adjacent side, that is ER divided by this hypotenuse, that is I into R divided by I into Z, I and cancel. This is equal to R by Z. Cos phi is equal to R by Z, or we can write Z is equal to root of R square plus XC square. If you are interested, you can find out this as Xc in terms of 1 by C omega. Okay, a lot of numericals can be asked in the competitive examination based on this power factor and the impedance, etc. Therefore, this cos phi is equal to R by Z. This is the power factor of the RC circuit. In the next class, we discuss the AC through the LCR circuit. Thank you very much.